Okay, cool. So before we start, the way this is going to proceed is that I'll be explaining a few basic concepts. Although these concepts would not be tested on in much detail, but these concepts are fairly necessary to do what's going to be on the final. So I'm going to like quickly go through these concepts first, and then we'll look into topics that you will see in the final and do some examples that are like directly taken from past finals. So they'll be fairly representative of what you can see in the final. And if you have any doubts, if you think I'm going too fast or if it's too slow, feel free to unmute yourselves at any point and then just like let me know, because it's hard to like keep on looking at the chat. So feel free to unmute yourselves. So I hope that's fine with everybody. If anybody has any questions on how we're going to proceed, like, okay, cool. Okay, so we'll be starting with a few basic concepts. First, we'll start with the budget line. So budget line is just you have a given amount of money, you have two goods in the economy, you have two given prices, and budget line is just how you spend your money between those two goods. So it's price of one times x1 is the amount of goods you buy, x2 is the amount of good two you buy, and p2 is the price of good two, and m is the total budget you have. So the line is representative of how you spend your entire money. So money is constant throughout the entire line, and the slope of the budget line is minus price of one times price two, minus because it's downward sloping. Okay, and the shaded part is basically the budget set. So it's not necessary that you spend the entire money you have. So budget set is just if you spend some of the money you have, and this is what the diagram looks like. And you can also have some changes in the budget line. So for instance, if your income increases, so M is your income, if it increases, it's a parallel shift towards the right, because now you can buy more of both goods, and but it doesn't change your slope at all. So the prices are still constant. The second change that can happen is if there's a change in price of one of the two goods. So let's say the price of good one falls down, then your budget line would tilt towards the right on the first good, because now you can buy more of good one given the same amount of income you had, because the price of good one fell down. Uh, in this second situation, so let's say the price of good two rises and the price of good one falls. In this case, there would be two tilts. The budget line on good two would fall down because the price of good two increase. So you can buy less of good two now. And the price of good one fell down. So you can buy more of good one now. So it goes from the black line to the red line. And in this situation, compared to the income shift, your slope will change because the prices are changing. Okay, any doubts on that? Okay, cool. I'm trying to go through these a little quick because you won't be tested on these, but these are just basic concepts that are like that you need to know. Okay, there are also other changes such as like you can get coupons, you can discount coupons for cash, you can discount coupons for goods. This won't be tested in the final to that extent. I haven't seen a question yet in the post final, so don't worry about that. What you can be tested on is you can have multiple constraints. So in such situation, let's say one of the constraint is your income, and the other constraint is, let's say, calorie count on food. So you plot both the constraints for both the goods, and then it's the intersection of both the constraints. So the orange shaded line would be your budget line, and then the shaded part would be your budget set. So you can see some questions, but these would be fairly simple. You just have to plot two equations, and that's it. Okay, so that's all on budget line. You don't need anything uh, else in terms of that topic. Okay, now let's look at preferences. So you have three kinds of preferences: strict preferences, weak preferences, and indifferent preferences. For strict preferences, it's simple. Uh, if X is a bundle and Y is another bundle, I strictly prefer bundle X over Y because it gives me a higher utility. So that's just a simple concept. Weak preferences, that is, you again have two bundles, but bundle X is either, it either gives me more utility or the same amount of utility. So you don't really prefer it strictly, but you might prefer it because it might give you more utility. So it's greater than or equal to, so that's the symbol. And for indifferent preferences, it doesn't matter which of the two bundles you choose, you're indifferent between both. Uh, and these are just the conditions. It's like a mathematical notation. Like you can also understand it simply in terms of words. Yeah. Okay. So let's talk about monotonicity. So the three types of monotonicity is weak, monotonic, and strongly monotonic. Weak monotonicity. So you'll see a lot of like mathematical notations, but I think it's easier to understand in like simple word terms. So for weak monotonicity, so it basically says more of something never hurts. It doesn't make you better, but it'll never make you worse. So let's say you have two bundles, uh, 4 5 and 4 4. So the bundle 4 5 might make you happier or might keep you indifferent, but it will never lower down your utility. So this can never happen, but it'll definitely either make you a little better or you'll be indifferent. So that's weak monotonicity. Monotonic preferences, on the other hand, so strictly more of everything. That means if you have a bundle 3 comma 4 and strictly more of everything, let's say 4 comma 5, this bundle will make you strictly happier than this bundle. But in this situation, you have no idea. So let's say the bundle 4 5 is still the same, but on the other hand, you have 4 comma 4. So in such a situation, you have no idea what your if you'll be strictly happier or not, because monotonic preferences says that strictly more of everything. So this doesn't have more of everything, it only has more of good too. Okay. And strongly monotonic preferences are just strictly more of something without changing the other one. So you go back to the first example and you just remove the equal to sign. So the bundle 4 5 will now make you strictly happier compared to the bundle 4 4. So I think it's just easier to understand in terms of words rather than mathematical notations. So yeah, but I don't think the prof has ever asked a question on monotonicity in the final, but like, just in case. Uh, okay, now on convexity. So the way you measure convexity is you take the indifference curve, you take any 2 points on the indifference curve, you join the 2 points, and then you take any bundle on that line. So you have two types of convexity, convex and strictly convex. Convex is just that. So let's say you join the dots A and B. So any bundle on A and B would either be strictly preferred or would either be preferred or you would be indifferent compared to a third bundle on the same indifference curve. So these are just example of substitutes and complementary goods. So you see, if I join A, B on both of these indifference curves, you'll still be on the same IC. So you can also be uh, not indifferent. So if I connect A and C here and I compare it to B, you see that any bundle on A and C would make me more happy, right? So yeah, but it's not always the case, hence the symbol greater than equal to. Uh, strictly convex on the other hand, so you have an indifference curve, again you join 2 points and you take an average bundle on them. So any bundle on AB would give you a higher utility compared to, let's say, bundle C. So that's strictly convex. Okay, and these are just some general cases of certain types of preferences. So perfect substitutes, it's just a linear equation. So that's going to be your indifference curve. Uh, so let's say your utility function is alpha times x1 plus beta times x2. So your slope is just minus alpha over beta. It's similar to a budget line, but instead of budget, you have utility on the line. Uh, Perfect complements, it's a minimization function. So a lot of people get confused here, and it's better to like look at it through an example. So, okay, so let's say your ideal cup of coffee requires 2 creams. So for every cup of coffee, you require 2 creams. So and let's say X1 is coffee and X2 is cream. So a lot of people uh, write this as a minimization of X1 times 2X2 because 2 creams. So it's like kind of like a straight idea, but that's not how it works. And we'll see why. So let's say you have 1 coffee and 1 cream. So you just plug in one uh, and one here. Now you see you can't have one whole cup of coffee, right? Because you only have half the amount of cream required. So you can only have half a cup. So it's not 2 times x2, it's x2 over 2. Because uh, if you have 1 coffee and 1 cream, you can only have half a cup. So it's 1 comma 1 by 2, and the minimization of that would just be the minimum value inside, and that's 1 by 2. So that's something that people get confused with. So yeah. And then the third type of most common function that you'll probably see in a lot of problems as well is the Cobb-Douglas function, which is basically x1 raised to the power something and x2 times x2 raised to the power something. And this is a side note, you don't need to remember this at all. If you monotonically transform a function, then it doesn't change your preferences at all. So I can just take the log on both sides and it would give me this, but it's still the same set of preferences. You don't need to remember this. It's like just a side note. Okay, so I know that was pretty quick and a lot of information, but those were like just the basics that you need to know before we like actually go into the main topics and like main examples. So any doubts on that? Feel free to unmute yourself. Okay, great. Okay, so now we're going to start with utility maximization. Uh, and the way we're going to proceed is I'm going to explain what utility maximization is, what expenditure minimization is, and then we'll see one example which includes both. It's going to be a fairly simple example. It might be the first question you see on the final. So on the final, I'm pretty sure you'll see one question on intertemporal change, one question on consumption and leisure, and one Edgeworth box question. The fourth question, seen from the past finals, can either be on a budget constraint or a simple utility maximization problem. So yeah. Okay, so the idea behind utility maximization. Oh, wait, we have. Yes, I'm going to post this PDF. Don't worry, with the recording. Okay. So the idea behind utility maximization is you have a utility function and you want to maximize your utility given that you have certain restriction on your budget. And the way we do that is you compare the slopes of the budget line and you compare the slope of the indifference curves. So the slope of the indifference curve is just a marginal rate of substitution, which is minus the marginal utility in terms of x1 over the marginal utility in terms of x2, and the slope of the budget line is just minus price of 1 over price of 2. And we do that to basically find the tangency point between the two curves. You can also solve the same question using the Lagrangian, which is a more general form. So if you feel like taking marginal utilities independently is not possible, then just do the Lagrangian and that would give you an easier equation. I'll use both the methods just to be sure. But yeah, the idea is that you want the tangency point between the budget line and the indifference curve, which is point A. And if you see point B and C, they're also on the budget line, but they're on a lower indifference scope. So you can still achieve a higher utility by reaching point A. That's why we compare the slopes to find the tangency point, because at point A, both the slopes are equal. Okay, and before we go into the example, expenditure minimization is basically, so again, you have a given level of utility here. So instead of fixing your constraint, you fix the level of utility. So you're trying to minimize your expenditure, the amount of money you spend for a given level of utility. And the way you do that is, again, you solve two equations. But instead of one of the equations being your budget constraint, the first equation is your utility function, which is equal to some constant that we fix. And then the second equation again is slope of the budget line equal to the slope of the indifference curve. Okay, and any doubts on both of these concepts before we move into an example? Okay, perfect. Okay, so the example is as follows. You have a utility function x times y. You have a given level of income, that's 100. Initially, the price of one is equal to the price of two, which is equal to $10. And the new price of good one is $5. So the price changes from 10 to 5 for good one. And the question is, if the price of B1 changes to 5, what is the new bundle consumed such that you maintain the same level of utility? So you see, this problem has two things. First, we need to solve for the level of utility. And the second part is, now that we know the level of utility, how do we minimize our expenditure? Okay, so the first part is a simple utility maximization problem. So you have, you maximize your utility function, which is x times y, and your budget constraint is this. I've just written it in simpler terms. So it's x plus y equals to 10. And the first thing we do is we compare the slopes of the indifference curve to the slope of the budget line. So that's minus y over x is equal to minus 1 over 1. And that gives us x equals to y. And now we just use this relation and put it back in our budget constraint. Before I do that, if you want to use the Lagrangian method, which is a more general method that works for all sets of equations, this is how you would have done it. So you set your Lagrangian as your utility function plus lambda is just a constant, and it's lambda times your you set your budget constraint equals to 0. So I just take the 10 here. So that's x plus y minus 10 equals to 0. And that's how you set your Lagrangian. And then you take first order conditions, which is basically, I'll first differentiate the entire thing with respect to x. Then the second time I'll differentiate the entire thing with respect to y. And the third time I'll just differentiate the entire thing with respect to lambda. So if you differentiate it with respect to x, you get y plus lambda is equal to 0. So you get a value for lambda here. If you differentiate it with respect to y, you get x plus lambda equals to 0. You get another value of lambda. And if you just compare these two values, you'll again get the same relation between x and y. And the third one would always be just your constraint. So you don't need to solve the third one. Like, don't even bother it. I just did it to like show you it's always going to give you the same constraint.
I have a question.
Yeah, sure.
Above, where you wrote MRS equal negative y over x, so y and x are the marginal utility.
Yes, so
And
minus y, so y is just the marginal utility with respect to x. So if you differentiate the utility function with respect to x, so x is, y is a constant, so you just get y times 1, which is y. And if you differentiate it with respect to y, you get x times 1, which is x.
okay, and where did you get negative 1 and 1 from?
So negative, so this is minus the price of 1 over the price of 2, right? So
Okay.
it's 10 over 10. So that's my bad. I should have written it as minus 10 over 10.
Okay.
It's just going to be minus 1 over 1.
Thank you.
No worries. Yeah, so you get this relation, and then you just put this back in your budget constraint. So your budget constraint was x plus y equals to 10. You just put y equals to x, and you get a value for x, and you get a value for y. And then you just calculate your utility, because remember, our first goal was to find what level of utility we need to fix. And you get our utility function is x times y, so that's 5 times 5, and that's 25. So that's going to be a fixed level of utility. Okay, so the second part of the question is, now that the prices fall into 5, how do we maintain a utility at 25? So the first equation in this case would be, we fix our utility function x times y to 25, and that gives us our first equation. And then the second equation, so you see here the slope of the indifference curve hasn't changed because our utility function is still the same. So this hasn't changed, but the ratio of the prices minus price of one over price of two will change, because now you have a new price for good one. So now it's minus 5 over 10, and that gives you x equals to 2y. And you just solve equation 1 and 2, and you get y equals to 5 over root 2, and you get x equals to 5 root 2. And you'll notice that the utility for this bundle of good is again 25. So what we did was just fix the level of utility and then solved for our utility function. So this bundle 5 comma 5 is also known as Marshallian demand, and the bundle 5 root 2 comma 5 over root 2 is known as Higgsian demand. So those are just the terms we use for utility maximization demands and expenditure minimization demands. Any doubt on this example? Okay, cool. Now there's something called the substitution and income effect, and there are two types of substitution and income effects. One is Slusky and one is Higgsian. So Higgsian is what we just did, where we try to look at if a price changes. So if there's a new price, how do we maintain the same level of utility we had earlier? So how do we substitute between goods to maintain the same level of utility? That's called Higgsian substitution effect. Slusky substitution effect, on the other hand, sees that if there's a new price, how do we consume the same bundle? So instead of looking at the same level of utility at the new price, we try to find the same bundle at the new price. So they're two different things, and people sometimes get confused like what substitution effect it is. So just remember that if you have a new price, when you try to see how you maintain the original utility, it's Higgsian, and when you try to see how to maintain the original bundle, that's Slusky. And we'll see when we do examples from the past final, we'll see situations of both, and we'll compare what's the difference. Okay, these are just some special cases of utility maximization that you can just remember. Although I hardly see that you get substitutes and complementary goods in problems, but just in case you do and you don't want to solve the entire thing, this is uh, just a formula that you can keep in mind, and it'll directly give you your Marshallian demand. You'll mostly see either like a Cobb Douglas function or like a random function, which is like not a general case. So it'll just be, you can take any situation. So x squared plus 3y, it'll just be a random equation. So those don't have a general solution. So for that, you'll have to solve. But if you see any of these three cases, then this is, you can just blindly use these formulas. Okay. And before we move into the next topic, there's something called compensating variation and equivalent variation. In simple terms, let's say you have an amount of income M. Compensating variation is just the amount of money you need to maintain the same utility at the new price. So this is directly related to the Higgshian demands we find, which is we try to maintain the same utility, but at a new price. And but the focus here is not the bundle we get, but the focus here is we try to see for that bundle of Higgshian demand, what's the additional money that we need. So that's the purpose of compensating variation. And equivalent variation is just you again see what extra money you need, but this time you try to see how do I maintain the new utility. So the utility we get after the price has changed, uh, but now we try to find the new utility at the old price. So that's equivalent variation. So again, CV is just same utility at the new price, and EV is just new utility at the old price. And we'll see, you'll definitely see one part of a question asking you to calculate the CV and the EV in the question, and we'll see how that works out.
Hi, sorry. I think the prof once mentioned that the CV and the EV were the same when the utility function was a Cobb-Douglas. Is that right?
Uh, I mean, that's usually right, but you have to consider certain assumptions under that. For instance, like I think the ratio of the powers have to add up to one or something like that. But it doesn't matter because even if it's the same, like the process of getting CV and EV is constant. So even if it's same or different, it doesn't matter. You will get the right answer the way we'll solve it. So don't worry about that.
Okay.
Okay, so now, so you'll definitely find one question on consumption and leisure. Uh, and okay, so before that, the way this topic goes is you have a certain amount of hours available to you, and you can split those hours between work and leisure. So you can either work or you just like spend your time not working. Uh, you also have a consumption demand. So I, as a consumer, want to consume some goods in the economy. And I think the professor always assumes the price of consumption is equal to one. So don't worry about that. And you have certain wages. So you get a certain amount of wage if you work. Or you have to pay a certain amount of income tax. You might also have to pay a lump sum tax. And you also might get some transfer income, which is like, so let's say you get holiday money. So that's an example of transfer income. And then so your utility function is a function of what you consume and what's your leisure, and you try to maximize that uh, in a setting where your constraint is as follows. So C is just the consumption. uh, I didn't write price of C times C because price of C is usually assumed as one. uh, and your consumption is basically equal to what you earn, right? How much money you have. And that's just, so H is the amount of hours you had, and L is the amount of hours you choose not to work. So H minus L is the total amount of hours you'll be working in the economy. So this is the amount you work times your wage, because number of hours you work times your wage is how much you'll earn. And then 1 minus T is just removing the effect of the tax you'll have to pay. So let's say that income tax rate is 20%. So 1 minus 20% is 80%. So whatever I earn from working, only 80% of that would be available with me to spend on goods. So that's your income minus if you have any lump sum taxes that you need to pay. Lump sum tax is just a fixed amount that is independent of how much you work. So it's a lump sum amount. Plus, if you get any lump sum money, and if you rearrange that, it gives you this equation. So C plus L is leisure times W times 1 minus T. So W times 1 minus T can also be interpreted as the price of leisure. So it's price of C, which is 1, times C, plus price of leisure, which is W times 1 minus T, times leisure, is equal to H times W times 1 minus T, which is the total hours you have times the wage minus whatever money you're paying plus whatever money you get as a transfer payment. So that's your budget constraint. Like, does that make sense? Okay, cool. And you'll mostly see two types of questions in the exam. Uh, First, where the professor plays with the wages, or second, the professor can play along with the taxes, or like any transfer payments, basically. Uh, I don't think I've seen a question ever where both of the things change, because that gets a little confusing, but you'll definitely get either of the two situations. Okay, and before we move into the examples, I'll also quickly explain what intertemporal change is, and then we can do two examples, one on intertemporal change and one on uh, uh, consumption and leisure, and we'll see all the different subtopics that you can see in the same question. Okay, so intertemporal change is basically, again, you have two goods, but instead of consumption and leisure or good one and good two, the two goods here are consumption today and consumption tomorrow. So let's say you have an initial endowment, W, which could be anything, like it could be the number of potatoes you have today, the number of the money you have today. It can be anything. So you have a fixed endowment today, and R is basically the rate such that, so if I have 1 unit of something today, it will give me R units of that good tomorrow. So let's say I have $10 today, or let's say I have $1 today. Tomorrow, that $1 would give me R dollars. So that's how R is interpreted. And you try to see uh, how do you split your endowment between consumption today and consumption tomorrow such that your utility is maximized. So your utility would, so the problem that we have is you have to maximize the utility function, which is a function of consumption today and consumption tomorrow, such that your consumption tomorrow, which is C2, is equal to, so W minus C1 is whatever was left after you consume whatever you consume today. So let's say I consume C1 today. So W minus C1 is just what I have left for tomorrow. But it will also be growing at a rate of R. So that would be the total consumption that I can have tomorrow. So that's the constraint. Uh, and yeah, so that's the problem that we have at hand, and it's just a simple utility maximization problem. Any doubts on that before we move into questions? Okay, cool.
Looks good,
Okay,
thank you.
so these questions are directly taken from the finals. So they're almost, like, I would say 85 to 90% representative of the type of questions you can actually see on the final. And like all the examples after this are like directly taken from past finals. So if you understand these questions, uh, I think you'll have a good idea of what you'll see in the exam, and like there won't be any sudden surprises. Okay, and if you feel like I'm going too fast with these questions, let me know, because it is important that you understand like each and every part of this question. Okay, so the question is as follows. Anne has 100 hours per week, which you can divide between consumption and leisure, and you have a utility function, which is 4 root c plus L. You have a certain amount of hours, right? And again, the price of C is 1. I think this is almost always true for every question the professor puts. Just makes it easier. Uh, and your hourly wage is 10. So the first question is, how many hours will Anne choose to work? So let's see. So, and again, you have 100 hours. Always keep in mind that you will always have an endowment in the question, because without an endowment, you cannot solve the question. Okay, so you have a utility function, you have a given wage, You have the price of C, you have 100 hours, and so again, T is income tax and capital T is lump sum tax. There's a reason I'm using a general notation, and I'll explain why. But if you, before you start a question, and this is a general tip that applies to every question, if you do not see taxes in the entire question, don't even bother writing the variables T and capital T. Just forget them. Just put them as 0 and solve your entire problem. The only reason I wrote it here was because if the entire question has changing values for T and capital T, if you find a general equation, all you have to do is plug in the values every time, so you don't have to solve the maximization problem again and again. So let's start with the problem. So you have a utility function 4 root C plus L, and you want to maximize such that your constraint is this. So again, C plus L times W, 1 minus T, equals to 100, which is your endowment, times the wage, 1 minus T, minus capital T. And it's the same process again. So you compare the marginal rate of substitution. So that's marginal utility with respect to C over marginal utility with respect to L, equals to minus price of C over price of L. And if you notice, the price of L is just what you see here. So that's W times 1 minus T. And when you solve this, you get a relation between C and W. That's this. So we know our wage is 10. We know our income tax is 0 and a lump sum tax is 0. I just put in these values here, and that gives me a value for C. Now, if you notice that if I had a value of T equals to, let's say, 0.2, all I had to do was put 0.2 here. And let's say if the next part asked what happens if I change T to 0.4, I wouldn't have had to solve the entire problem again. I would have just put 0.4 here. So you see, if you write it in general terms, it makes your question easier. But since you have no taxes, if you have no taxes in the entire question, don't bother writing the variables. Okay, so yeah, you get a equation for C. You just plug in the value. Yeah, go ahead.
Can you go up a second? A little up. What's that? Like C equals, what is that? Is that, what number is that? Is that 4? Like below.
Oh yeah, that's 4.
Okay.
Yeah, I just solved this equation, and you get 4 times W times 1 minus T whole square.
And so when it's equal to the price of the consumption over the price of leisure.
The price of the leisure, yeah. It's the same as any utility maximization problem. So it's minus the marginal utility of X over the marginal utility of Y equals to minus the price of X over price of Y. Your X and Y have just changed. That's it. Okay. So you get a value of C, and then you just put your C in this constraint, or like this equation that you found. Either way, you'll get a value for L as well. So again, you have 2 equations. This is the first equation. This is the second equation. You have 2 variables, that's C and L, and you just solve 2 equations with 2 variables, and you get a value for C and L. So I just plugged in this value in our constraint. So that's 400. So that was C plus L times 10. So that's L times wage is 10. Tax is just 0. So this is just 1. So that doesn't matter. Is equal to 100 times the wage, which is 10. And 1 minus T again is just 1. And there is no lump sum tax. So you get a value for L by solving this. And now you have both the values. So A, you can calculate the working hours. So that's just 100, which was your initial endowment, minus the time you do not choose to work. So that's your leisure. And you get 40. So you work 40 hours. So that's that's what the question was asking. But what I also always do is calculate the amount of utility for the bundle we just got, because you never know, the questions later might ask for this information, and then you don't have to go back, figure it out again, stuff like that. So whenever you find a bundle, even if the question is not asking, always try to find the level of utility for that bundle. I know it takes like 10 to 15 seconds, but it might be useful for other parts of the question. Okay, so for this bundle, our utility is 140. Okay, so that was part one. Let's do part two. So if Anne's hourly wage is raised to 15, how many hours will she work? So now you have the same maximization problem again. The only difference is now your wage instead of 10 is equal to 15. So what do? I just plug in the value of W as 15 here. And I don't have to solve this problem again. So you see, the wage is 15. Again, tax is 0. Lump sum tax is also 0. I just put in the value of W as 15, and I get the value of C as 900. And I put this in our initial budget constraint, and I also get a value for L. So if the wage increases to 15, the amount of working hours now have also increased. So again, working hours are just 100 minus the times you choose not to work, which gives you 60. So for this new bundle, your utility now is 160. So you see the utility has also increased. Again, the question didn't ask what level of utility is there. I just calculated anyway because it's sometimes useful for later parts. Okay, any doubts on that? Okay, cool. Okay, part 3. This is where it gets interesting. So let L1 be the number of hours you work that was determined in part 1. So in part 1, we were working 40 hours. So L1 is 40. Suppose that the hourly wage is $10 if Anne works no more than 40 hours. So from 0 to 40 hours, if Anne is working, she only gets $10. But it increases to $15 for every hour after 40 hours. So for the 41st hour, for 42nd hour, up until hour 100, Anne can get $15. Now, how many hours will Anne work under this new system? Okay, so let's see. So you have L1 as 40. Again, taxes are 0. So if wage is 10, right? So that means you are working under 40 hours, right? Because wage was 10 from 0 to 40. But if you're working 0 to 40 hours, that means you are not working for the other 60 hours or more than that. Is that part clear? I just want to make sure that that part's clear because that's really crucial. Okay, I'm going to take that as a yes.
Do you mind repeating what you just said?
Sure,
I
no
didn't
worries.
hear.
Yeah, so the question says you get $10 if you work between 0 to 40 hours. So if you're working 40 hours, you get a wage of 10, but that means you're not working for 60 hours, right? So L is 60. But now let's say instead of 40 hours, I decide to work 39 hours. I still get a wage of 10 because it's under 40, but now I'm not working for 61 hours. So that's a leisure of 61. So you see, for any amount of hours that I work between 0 and 40, my amount of leisure is 60 hours or more. So if my wage is equal to 10, that means I'm working below 40 hours. And I can just rewrite that statement as I'm not working more than 60 hours. And the same logic goes for if your wage is 15. So if my wage is 15, that means I'm working more than 40 hours, because that's what the question says. If you work more than 40 hours, you get a wage of 15 for every hour you have worked after 40. But if I work more than 40 hours, so let's say I'm working 40 hours, right? That means my leisure is 60. As I increase my working hours from 40 to 41 to 42 to 43, my leisure keeps on falling from 60 to 59 to 58 to 57, because leisure and working hours are opposite, right? If I increase the amount of hours I work, I'm simultaneously decreasing the hours I spend on leisure, and also vice versa. So this just translates that my leisure would be less than 60 because I'm working more than 40 hours. So these are the two situations you can get for your wage. Now let's see how our budget constraint would look like in such a situation. So if your leisure is greater than or equal to 60, you get a wage of 10. So I just put 10 in the budget equation, and that gives me this. Pretty simple. Where it gets difficult is this, because what a lot of people would do is you write C plus 15L, that's fine. But for the right side of the equation, you can't just put 15 and get 1500. The reason for that is you don't get $15 per hour for all your hours. You only get it once you've crossed the threshold of 40 hours. So the way we form this budget equation is as follows. So up to 40 hours, you get $10, right? So for the 40 hours you've worked, you get $10 for sure, because we are only interested in the interval where you have already worked 40 hours, and now you see what happens if you work more than that. So since you've already worked 40 hours, you have already earned 40 times 10, which is 400. And now you see, for the remaining 60 hours that you have, you subtract the amount of leisure you would choose out of those 60 hours. So out of the 60 hours, I choose L hours of leisure. So 60 minus L would be the amount I choose to work after 40. And that for that amount of hours, I get 15. And if you solve this, this is the budget constraint you get. That is this part clear? Because this is like the most confusing part about this question. I can repeat this again if even one person has a doubt.
I have a question.
Yeah, go ahead.
The budget, what, this is a function, right? Like the budget constraint. I'm
Yeah.
wondering what this function is supposed to give. Like, what's the output? Is it C?
Yeah, so you remember when we solve a maximization problem, you have two equations that you need to solve, right? One is your utility maximization function, for which you compare the slopes, and the second equation is the budget line. But now you don't have one common equation for the budget line. You have two different equations in two different scenarios. So that's the reason your budget constraint is split into two parts, because you need to consider both the cases separately.
Okay. Question. You said that we could get also a question like this, but where not the wage, but the taxes change.
Yes,
Uh,
I'll be doing that next. So I'll cover
okay.
both of the equations. Don't worry.
Okay.
Yeah. Okay. So yeah. So
Sorry, I have a question too.
yeah. Go ahead.
So what would the equation look like of the budget constraint if we had a tax?
If you had a tax, so this would just be L times 1 minus T, and again here in front of W you would have 1 minus T again, minus capital T. So it would just be the same as this equation right here. And then you plug in the values. You did do the same thing that we did. But I'm fairly sure that you would not get a question where the professor messes up with both the wages and the taxes. I have never seen a question like that on the assignment or on the final ever, especially considering the semester that we've been having. I do not think you need to worry about that. It'll either be just the wages being changed, or it'll be just the taxes being changed.
Thank you.
No worries. Okay, so yeah, so this is the equation you get for the situation where you choose your leisure to be less than 60, or in other words, you choose to work more than 40 hours. Remember, we're splitting the situation into two parts: A, where you work 40 hours or below, or you work 40 hours or more. Those are the two situations we are splitting our constraint into. For less than 40, it's a simple equation. But for more than 40, we need to take into account that we have already worked 40 hours. And for those already worked 40 hours, we have already received a wage of 10 per hour. And now we see for the remaining of 60 hours, how much we work. And for those hours, we get a wage of 50. So this is your budget constraint. And now you have two cases. The first case is you work less than 40 hours. And you see, we've already solved this in part one, right? Where your constraint is C plus 10 times L equals to 1000, and your utility function is the same. And we solved this in the first part, and we have our bundle, and we also have our utility. And you see how I said calculating the utility does help in later parts. So for this, you have a utility of 140. This is the case that we need to solve for this part. So your utility function is the same, but your constraint now is, it's my bad. This is supposed to be 1300. That's an error. I'll just note it down to make sure I correct it when I upload the slides. Okay, so my bad. This is supposed to be 1300. And then you solve the utility maximization problem like you would solve any other problem. You get one equation from this, and you plug it back into the budget constraint, and you get L as 26.67, and you get C as 900. So your new utility in this case is you just plug in the values in your utility function, and you get 146.67. So you see, between these two cases, Anne chooses to work more than 60 hours because that gives a higher utility. And the working hours would just be 100 minus L, which you found as 26.67, and that gives you 73.33 hours of working. Is there any doubt about that part?
Yeah.
Yeah.
So I'm not 100% sure about what you did here. So case one is just the first equation, right? And you found the utility.
Yeah.
Right?
So case one is just we work less than 40 hours. So it's this case.
Okay. But
Yeah.
how did you find L there?
So you see this exact problem, maximizing u equals to 4 root c plus L such that c plus 10 equals to 1000. This exact problem we already solved in our first part. Our first part was exactly the same two equations. So you don't have to solve that again.
Okay.
Yeah. And then what you have to solve this time is this second case where your constraint has changed. Again, this is supposed to be 1300. That's my bad. I messed up literally in the most confusing part.
Okay.
But yeah, and you choose to work more than 60 hours because it gives you a high utility.
Okay.
Okay, and then we look at the last part, which says decompose the total change into Slusky substitution and income effects. Notice the word Slusky, it's not asking for Higgshian substitution effects. And I'll give you a step-by-step explanation on how we solve Slusky substitution and income effects. Because for Higgshian is just an expenditure minimization problem, which we did in our previous example. Okay, so for a Slusky substitution effect, I always follow a three-step solution. The first is you have your original maximization problem, which was the first part where nothing changed. It was just your original problem that you had. And for that, we had our C equals to 400 and our L equals to 60. Now we go to the second step. I don't know why I wrote the second step at the bottom, but yeah, sorry about that. But the second step you do is, now that your wage has changed to 15, you solve a new maximization problem with this setting. So you maximize your utility, same function, but now your constraint is different. You solve it with the wage of 15. So you have this equation, C plus 15, L equals to 1500, and you have utility equals to 4 with C plus L. I haven't solved it here again, but it's going to be the same process. First, you compare the slopes. So you get a similar relation between C. So I just plug in 15 here, and I get the value of C as 900. And I just put that here to get L equals to 40. So that's the bundle I would consume after the wage changed to 15. So again, step one is the original problem. Step two is you solve the maximization problem, but at the new price. And step three is now you try to see how would you consume the old bundle at the new price. Remember when we were differentiating between Higgshian and substitution effects, we said that Slusky substitution effect is where you try to consume the old bundle, not the old utility, at the new price. So, so let's see what the old bundle was. That's 460, and you just plug in that into your budget constraint, and you see you need 1300 of income. So for your old bundle at the new price, you need $1,300. Now that you know how much you need, the last thing you need to do is solve your problem at a level of 1300. And that's it. So you have your income as 1300, your wage as 15, which is the new price, and you solve this, your maximization problem. And you'll notice that this is exactly what we solved in our last part here. It's the same maximization problem. And usually your professor will always do this, where it gives you the same maximization problem that you'll have to solve so that you don't have to solve it again at all. So every part will only ask you to solve one maximization problem. And if you have other ones, they would have already been solved in the previous parts. But otherwise, it would just be cruel. Okay, so now
Sorry,
yeah, go
I
ahead.
don't really understand how you found M.
So the third part is, like we said, so for Slusky substitution effect, you try to find how to consume the old bundle at the new price, right? So our old bundle is 460, but our new price is the wage of 15. So we see, if I want to consume this old bundle at a wage of 15, how much money do I need?
Okay.
And that's 1300. And once I have 1300, so now you know what money you need to consume that old bundle. Now I just use the same amount of money to see is there a possibility that with $1,300, I can get a higher utility with a better bundle? That's your last step. And for that, you just put M equals to 1,300, your wage equals to 15, and you solve this maximization problem, which you have already solved in the last part. So you already know that your answer for that is 26.67 and 900. And now you compare your substitution and income effects. So you went from, your total change was from, we need to compare the effects only in terms of leisure. The question doesn't ask about consumption at all. So we went from 60 to 40. But in doing so, the first thing that happened was we substituted ourselves from 60 to 27, and then from 26.67 we went to 40. So our substitution effect was what happened between the first two stages. So by first two, I mean when we substituted. So we went from 60 to 26.67. So we went down minus 33.33 units. So that's your substitution effect. And then from 26.67, you finally go to 40, which is, so 40 minus 26.67, that's 13.33 units. And you see your total change from 60 to 40 is a negative 20, right? And if you add these two, that would just give you the same answer, that is minus 20. Is there any confusion regarding that part?
I have, it might be a dumb question, but I don't understand why in the third part, you do the maximization problem such that C plus 15L equals 1300.
Okay, no worries. So
why is it not 1500?
yeah, so the 1500 part we solve at the second step, which is, now that I have a higher wage, I want to see that for this wage, what is going to be my bundle, right? So that 1500 problem is your second step where your wage has increased to 15. This step right here is asking for something else. It's saying, first, you look at how you consume your old bundle at this new price. So at a wage of 15, how much money do I need to consume the original bundle? And that gives me $1,300. Now that I know that I have $1,300, because remember, our original bundle was also consumed at the same amount of money. What I'm trying to do here is that, given that I have $1,300, I am trying to find, is there a better way to maximize my utility? Is there a way to get more happiness? So I solve the problem with the new wage, but I limit my money to 1,300 because I want to see that with the same amount of money, how do I substitute between two goods so that I can get a high level of utility? So that's all I'm trying to see in part 3 is, how am I substituting between the two goods given I have the same amount of money from the first bundle. And then I compare it to this 1500 part, which tells me that once I have substituted, what's the income effect of this increase in wage? If you also just see it logically, it tells you that when wage increased, the price of leisure also increased, right? Because the price of leisure again is just W times 1 minus T. So when your wage increases, it's costlier to not work because leisure is also becoming expensive. So you go down for leisure. So you reduce the amount of hours you choose not to work. So you see, you go from 60 to 26.67. But since wage has increased, you also earn more as you work. So it also increases your income. So you go from 26.67 to 40. So you see the substitution effect pulls you down because it makes leisure more expensive, but it also pulls you back up a bit because it allows you to earn more money. So that's the logic we are trying to figure out here. I hope that made sense.
Yeah, it did. Thank you so much.
No
Could
worries.
you just can I just take a look at the question once again? Just
Yeah,
real
sure.
quick. Thank you.
And don't worry, like I'll be uploading these like slides with the questions and everything.
Oh, okay, great. Thanks.
Yeah, no worries.
Okay, great.
Where will it be uploaded to? Like on Facebook?
Yeah, it'll either be on the ESA like main Facebook page, or it'll also be on the 250 econ group that's there on the Facebook, and also on the event page. So all three places, don't worry. And if you still don't find it, shoot me a text on Facebook. I'll send it to you. Okay. We we're not running behind time, hopefully. Okay. Now we look at a question where there's nothing to worry about wages, but now there's tax. And instead of looking at substitution and income effects, we look at compensating variation and equivalent variation. So you see, like, you'll have a broader question, and then there'll be like a small part which tests you on other subtopics. Okay, so let's read the question. Bob has 70 hours. That's your endowment. You have a utility function, which is root CL. This is supposed to be an equal to sign. The price of consumption is again 1. Your hourly wage is $5. And in addition to your labor income, you also receive $40 from your parents every week. So that's your transfer income, the holiday money that I was talking about. Okay. How many hours will Bob choose to work? Let's see. So your problem is you have a utility function, price of C equals to 1, your wage is equal to 5, you get a transfer income of 40, and you have 70 hours as your endowment. T is your income tax rate. I always mention the variables and what they mean, because like sometimes same variable can mean multiple things, but it's always good to write what the variable means. Okay.
Sorry, what is N?
M is
No, N.
N. I don't see an N.
N equals 5, I think.
Oh, that's W. That's my bad.
Oh, okay, sorry.
Yeah, it's I'm still trying to like write on a whiteboard. My handwriting is bad on paper anyway. Sorry about that.
No worries.
Yeah, so that's the question. And then now we solve the maximization problem. So you have your utility equals to root C times L, and your constraint is as follows. So you have C equals to 70, which is your endowment, minus L times wage times 1 minus income tax plus the transfer you receive from your parents minus lump sum tax if any. And we do the same step again. Your MRS is minus the marginal utility of C over the marginal utility of L, and you compare that with minus the price of C over price of L, which is minus 1 over W times 1 minus T. And solving this, you get C equals to W times 1 minus T times L. Again, it's always better to write in general terms, and in this question, you'll see why. For minus L over C, I just skip the like dirty calculus calculation part. But if you take derivatives for the marginal utility, this should be your end result. Okay, so now that you have this, the first part asks you have no income tax, Yeah, go ahead.
Wait, sorry, how did you get minus 1 over W times 1 minus T?
This, so okay, so
Yeah.
this is just minus price of C. So price of C is 1 over price of L. And if you see here, the price of L is just L times W times 1 minus T, right? So W times 1 minus T is just the price of L.
Okay, great. Okay, thank you.
W times 1 minus T will always be the price of L. So like, even if you don't want to like follow it logically, you can also blindly remember that fact. Okay, so
Okay, got it.
Yeah, so this is your problem. You have no income tax, you have no lump sum tax. You do get $40 from your parents, and your wage is 5. So once again, I just plug in the values here, and I get C is equal to 5 times L. And I use this relation, and I put it into my budget constraint, which is this. And you'll see you get a value of 39 for L. And you just put 39 back into this equation, and you get a value of C as 195. So your working hours are just 70 minus the time you choose not to work, 39. And
Sorry,
that
how
gives
did you get 39?
39. I just put C equals to 5L back into my budget constraint, into this. So you see 5L, so that's C, right? So we got C as 5L. I put 5L plus L times the wage, which is L times 5. There is no tax, so this is just 1, equals to 70 times the wage. So that's 70 times 5. Again, there's no tax, so this is 1. This is just 1. There's no lump sum tax. This is just 0. But now you get plus M, which is plus 40, the money you get from your parents. So I just plug everything into our budget constraint, and then you get the value of L as 39 if you solve this. And then using 39, I just put 39 into C equals 5 times 39, and I get 195. So yeah, and you get the working hours by just subtracting 39 from 70. And again, I always calculate the utility because at some point it'll be useful. So the utility from this bundle is 87.21. Okay, so we did the first part. Let's see the second part. The government implements a 20% tax now. So you have a 20% tax. Write down Bob's budget constraint. How many hours will Bob choose to work? And how much tax does Bob pay? So now you see, you don't have to solve the entire maximization problem again. All I can do is put wage equals to 5, tax equals to 0.2 here, and then get a relation between C and L. It would not be C equals to 5L anymore, and we'll see that. So in our budget constraint, I put C. So this, now the question first asks, what's our budget constraint? So that's the first thing we need to write down. So our budget constraint is C plus L times wage. Now we have a tax, so this is no longer equal to 1. So this is 1 minus 0.2 equals to 70 times the wage times 1 minus tax, which is again 0.2, plus the 40 we get, and there is no lump sum tax. So all I did here was plug in the values that we were given into our budget constraint. That's it. And you get your budget constraint as if you just solve this and like simplify this, you get C plus 4L equals to 320. So that's your budget constraint. So we did the first part that the question asks. Write down the budget constraint. Now the next thing the question asks is, how many hours will Bob choose to work? So it's just a maximization problem, right? We don't need to solve it again because we already found a general relation here. C is equal to W times 1 minus T times L. and I just plug in the values now. So C is equal to 5 times L times 1 minus T. And that gives me a relation between C and L. So instead of 5L, C is equal to 4L. And I just put this back into the budget constraint we have, and you get, so C was 4L, so 4L plus 4L equals to 320. You solve this for L and you get L equals to 40, and C is 4 times 40, so it's 160. And the question asks, how many hours will Bob work? So that's just 70 minus 40 and 30. So Bob chooses to work 30 hours now. And what's the utility we get in this case? It's, you just plug in the values in your utility function and you get root of 40 times 160. That's 80. So from a utility of 87.21, you went down to a utility of 80, and we'll see why that's relevant later. And the last thing the question asks is, how much tax does Bob pay? So it's an income tax, so you pay tax on the amount of hours you work. So I work 30 hours, I get a wage of 5 per hour. So I earn 30 times 150, that's my income. And the government says there's a 20% tax. So I pay 20% on the money I earn. So that's just $30. So I give $30 as income tax. And there we go, that was part 2. Oh, any doubts on that? Okay, cool. Oh, let's do part 3. Let T be the tax you calculated in part 2. So T is $30. If the 20% labor income tax that we had in 2 is replaced with this lump sum tax, how many hours will Bob choose to work? Which tax system does Bob prefer? So the first thing that the question asks is, how many hours will Bob work under this new system? And what's the new system? It's just, you remove all the income tax, you replace it with a lump sum tax. You still get $40 from your parents, and your wage is still 5. So let's see what the budget constraint looks like. So it's C plus 5 times L. There's no 1 minus T here because your income tax is 0. 70 times 5. Again, there's no 1 minus T here because your income tax is 0. Plus the money you get from your parents. But now you have a lump sum tax of 30 that you need to pay. And this gives you your new budget constraint, which is C plus 5L equals to 360. So that's a new budget constraint for this new system. And we don't have to solve the problem again because we already did. And we know that C is equal to W times L times 1 minus T. And since there is no income tax, this is just wage, which is 5 times L. So we get the same relation, C equals to 5 times L as the first part. You put this into the budget constraint you just got, and you get C, which is 5L plus 5L equals to 360. And you solve that, you get L equals to 36 and C equals to 180. So the question asks, how many hours does Bob work? That's just 70 minus L. So that's 70 minus 36. That gives you 34. So Bob chooses to work 34 hours now. But the last part of this part asks, which system does Bob prefer? So let's, and for that we compare the utilities. Bob will choose whatever makes Bob happier, right? So the utility at this bundle is 80.5. In the last question where there was no lump sum tax, instead there was an income tax, we saw that the utility was 80. So since here the utility 80.5 is higher than 80, Bob will prefer the lump sum tax system. And that answers the last part of part 3. Okay. Any doubts on that? Cool.
All good.
let's do part 4. Find the amount of lump sum tax that replaces the 20% income tax in 2. So we had a 20% income tax. Now we want to replace it with a lump sum tax such that Bob is as well as in part 2. So you see, this is kind of hinting towards expenditure minimization, where we see that at the new price, so price here is like at the new level of tax, how can we make sure that Bob maintains the same utility? And how many hours will Bob choose to work if this new lump sum tax is implemented? So this is just a Higgshian demand problem. So you see, we need to fix the level of utility at 80, that is from part 2, where we had the income tax. So we want Bob to have the same level of utility of 80. So that's 80 times 80 equals to root CL. So you get one relation from here. That's the first equation in expenditure minimization, right? So that's the first equation we get. And now we have to find a value for lump sum taxes. So I denote it as like T dash. We need to find the value for this such that I still get an 80 amount of utility. And how do we do that? We have the first equation. We have our second equation, which is our budget constraint. So our budget constraint is just C plus 5L because there's no income tax anymore. So there's no 1 minus T. 70 times 5, again, no 1 minus T, plus 40 minus T dash, which we need to figure out still. So I just leave it as a variable. So this is your budget constraint. And we also have our tangency condition, which is MRS equals to minus price of C over price of L. And price of L is just W times 1 minus T again, but there's no income tax, so it's just W. So minus 1 over 5. So you get C equals to 5L. Now, if you see equation 1 and 3, which we usually solve for an expenditure minimization problem, that gives you a value for C and L, right? So if I solve this equation and this equation, it's 2 equations in 2 variables. It gives me a value for L, and I just put that value here and also get a value for C. So 2 variables, 2 equations, we solve that. And you get these values, and these values give you the same utility as 80. And that's what we're trying to find, right? So what's the working hour here? It's just 70 minus L. So that's 34.22. And now the question was asking, what's going to be this new lump sum tax that we need so that Bob can have the same level of satisfaction equals to 80. And we just found the values of C and L. We just plug it back into our budget line. And now we can solve for T dash. And that gives a value of T dash as 175.33. So what we just did was basically we fixed the level of utility. We found C and L, and we found a value for a lump sum tax such that instead of charging an income tax, I can charge a lump sum tax, and Bob will still have the same level of satisfaction. That's what we did in this part. Was there any doubt regarding that? Okay, cool. Let's do part 5. So you have 20% tax on labor income in part 2, and Bob's parents want to give him some extra money, just enough to offset the impact of this tax. So again, you have 20% income tax, but what's happening now is that your parents want to give you money such that you remove the impact of this tax totally, right? So let's see how we do that. So remember, when you had no tax at all, that was part one, right? Your utility in this part was this. So Bob's parents want to give him money such that his utility is still at this level. Once again, calculating utilities always helps in other parts. So that means the utility still needs to be 87.21, right? Or like root 195 into 39. And we maintain this utility, but by giving him more money. And we see how, and let's see how we do that. So again, it's an expenditure minimization question. You fix the level of U at root 195 times 39, and that has to be equal to root CL because that's a utility function. And you get the first relation, the second relation you get from comparing the slopes, and we saw that was C equals to W times 1 minus DL. Tax is 20% in this question. Therefore, we just plug in the values and we get C equals to 4N. So again, we have two equations. We solve the two equations, two variables. You get L equals to 43.6 and C equals to 174.41. So now you have the values of C and L such that you have maintained the original utility where there was no tax. And now we just plug. Yeah, go ahead.
Sorry, I have a question. For the equation for C, where did you get 195 and 39?
Yeah, sure.
Or
So
for the utility?
yeah, so we need to see. So the question says it needs to offset the impact of the tax. So in question one, in part one, there was no tax, right? So when you say you want to offset the impact of tax, you're basically saying that you want to maintain the same level of satisfaction that you had when there was no tax. And that was our part one solution, right? So in part one, there was no tax, there was no lump sum tax, and we want to maintain the same level of satisfaction. So our satisfaction in this case was under root 195 times 39, right? So I just fixed that level of satisfaction here. So we want the same satisfaction. And that's where this value comes from.
Okay, makes sense, thanks.
Yeah. And then I just solve these two equations. I get values of L and C. And just like we did in what we did in the last part to find the T dash, we do the same thing to find M dash, which is how much money does he need to offset the amount of this tax that Bob has to pay. So again, I just plug everything into the budget. Yeah, go ahead.
How did you go from C equal W time 1 minus T time L to C equal 4L?
Yeah, okay, so your wage is 5, right? So your wage is 5 and you have a tax of 20%. So it's just 5 times 1 minus 0.2 times L.
Oh, okay, great. Thank you.
Yeah, no worries. And that gives the values of L and C. And I just put it back into my budget constraint and find the value of M dash. So that gives me M dash equals to 68.62. So what this tells me is that if I want to maintain the same satisfaction as this when I had no taxes, I would need $68.82 of money from my parents to offset the impact of the tax that has just been put on me. So I need $68.82. But how much is the additional amount that I need? So this is the amount I need, and I was already getting $40 from my parents. So I need 68.82 minus 40. That's I need 28.82 more dollars than before from my parents. So that's the answer we're looking for, is 28.82. And let's see what the last part asks. Relate your answers in 4 and 5 to some of the measurements of welfare changes. So compensating variation and equivalent variation. And you'll see the compensating variation. What was the compensating variation? Let's see the definition again. That's the change in money you needed to maintain the original utility. Remember what our original utility was in part 1? That was root 195 times 39. How much money we needed to maintain this at the new price. And by new price, they mean the tax that was introduced. So, and we saw this is just what we solved in question 5, right? We had the utility fixed at the original level, and we solved it at a tax level of 0.2. So this change in money is just, this answer for CV is just 28.82. We've already calculated it. And let's see what the definition of equivalent variation was. It said it's the amount of money, the additional amount of money that was needed to maintain the new utility. And what's the new utility? Remember, in part 2, when the tax was introduced, our utility shifted from 195 times 39 to a utility of 80, right? So 80 was our new utility. Now the question asks, how do we maintain the new utility of 80 at the old price? And by old price, they mean no taxes, right? And if you see, we already solved this in part 4, where we fixed the level of utility at 80 and there was no tax, right? But this, the change in money was this negative tax, lump sum tax that we had to pay, right? And we got the value as 175.33. So your equivalent variation would just be minus 175.33. The minus sign is there because it's a tax. So the change in the money is negative because you are reducing the money you have. Is there any doubt regarding that?
Wait, can you explain again for EV?
Sure. So the definition of EV says that it's the change in money that you need to maintain the new utility. So the new utility here is 80, which was what we get, which is what we got when the tax was introduced, right? So when we had a 20% tax in part 2, our utility went to 80. So that's a new utility. How do we maintain this new utility of 80 at the old tax of 0, right? And we solved this already in part 4, where we say we fix the level of utility at 80 and the change in, and the income tax is 0, and the change in money is just the lump sum tax that we now need to pay, and we get that at once as 175.33. So the change in money is just minus 175.33, and minus is there because the change is negative because it's a tax, so we are paying it out of our pocket, compared to CV where we were receiving the money from our parents. I hope that makes it clear.
Yeah.
Okay, perfect. Wait, let me see how much time we have. Okay, I think we have time. Okay, so another thing to notice here is that compensating variation just tells you the substitution effect, but this is the Higginson substitution effect compared to the Slusky that we saw in our previous example. And what's Higginson substitution effect is, remember, it's how we maintain the original utility at the new price. So at t equals to 0, this was our original bundle, right? The first part we solved. At t equals to 0.2, what was our compensating variation bundle? And you remember our compensating variation bundle was just this part we solved, which was 28.82, where we tried to figure out how we maintain the same utility at the new price of 0.2. So at this level, our bundle was this 43.6 and 174.41. So that was your CV bundle. And then your final bundle was what we solved in part 2, where your tax was 0.2 and we get our new utility of 80. So you see, we go from the original bundle to the final bundle, but the CV bundle in the middle tells us our Higginson substitution effect. So we go from this bundle to this bundle, that shows our substitution effect. And then we go from this bundle to this bundle, that shows our income effect. But this is the Higginson substitution income effect compared to Slusky. And once again, the difference was that in Slusky, we look at how to consume the original bundle at the new price. But in Higginson, we look at how to consume the original utility at the new price. So that's the difference. Okay, and now we move into our example for intertemporal change. This is relatively a little easier because you can only mess with a few things. It's mostly the rate, or there might be one sort of lump sum transfer, but there won't be like taxes or wages. It would always be in the terms of goods you have. So you don't have to worry about multiple variables here. Okay. Before we move into that, any like doubt, or if the pace is fine, if I'm moving too fast, too slow?
Sorry, I have a general question.
Yeah, sure, go ahead.
Is the budget constraint, like the equation that you wrote, is it always the same for every equation?
What do you mean, like same? For the questions on
The
consumption,
general formula.
yeah. So the idea behind a budget constraint is that whatever you consume should be equal to the money resources you have, right? So for instance, in a consumption and leisure question, whatever I consume, so that's C, and the price of C is 1. So it's just 1 times C. So price of C times C, that's what I consume, right? But I can only consume from what I earn. And what do I earn, which is like the money that I have in the end, is 70, which is my endowment of hours, minus what I do not choose to work. So 70 minus L is just what I choose to work, times the wage. So that's what I earn when I work, times 1 minus T, which reduces my income a bit because I have to pay some taxes, plus M is the money I get from like anyone, like parents, friend, anyone, minus a lump sum tax. So the right hand side of this equation just tells me how much money I have with me, and the left side of the equation tells me what do I spend that money on. That's the general concept of a budget constraint for any question you have. I hope that answered the question.
Yeah, thank you.
Okay, so now we look at the intertemporal question. So in this question, instead of two goods, or like consumption and leisure, you only have consumption, but between today and tomorrow. So let's see what the question reads. You have Bob, who lives for 2 periods. in a cottage next to a pond. The pond has 600 pounds of fish in the first period. So today you have 600 pounds of fish. The fish in the pond reproduces at a rate of r greater than 1, where so r is just so if I have one fish today, I get r times 1, so I get r fishes tomorrow. That's r. And so if I have 600 pounds and I eat 100 pounds out of it, next period I get 500 pounds times r. That's how r works. You have a utility function that's root c1 plus, so delta is just 0.5 in this question, so root c1 plus 0.5 root c2, that's a utility function. Okay, let's see what the first part asks. If Bob takes care of the pond by himself, r is equal to 2. How much fish does Bob consume in the first period and in the second period? Okay, so you have a utility function. You need to maximize this. Yeah, so in this case, your budget constraint is not in terms of money, right? Because you don't have money or goods in this question. So the budget constraint here is the following. You have a certain consumption tomorrow, and what you consume tomorrow is just r times what you did not consume today. So out of 600, if I consume C1, then I have 600 minus C1 units left, right? But tomorrow, that would give me R times that amount, because R is the rate at which it grows from one period to the next period. So that's your budget constraint. And I just rewrite that like in terms of R on one side and C1 and C2 on the other side. I just simplify this equation. So that's your budget constraint. And now you do the same thing like that you do for any maximization problem. You take the MRS, so marginal utility of C1, that gives you 1 over 2 root C1 over the marginal utility of C2, that's 0.5 times 1 over 2 root C2, and that is equal to minus price of C1 over price of C2. Now this is where it gets tricky. So price of C1 is just 1, right? So let's say the price of C1 is 1 today. What's the price of C2 today? So if I tell you that one fish today gives me R fishes tomorrow, then one fish tomorrow is just 1 over R fishes today, right? Does that make sense?
Can you say that again, please?
Yeah, okay. So actually, let me see if I can open a whiteboard and explain it. That would make it much easy. Wait, can you see my whiteboard?
Yes.
Okay. Okay, so the way it works is, so let's say this is tomorrow, okay, and this is today. So one fish today gives me R fishes tomorrow, right? That makes sense, right? Okay, so if our fishes tomorrow are worth one fish today, then one fish at C2, so one fish tomorrow is just 1 minus R today, right? Because if I have 1 minus R today and I want to see how much I get tomorrow, I just multiply this by R, right? And that just gives me one fish tomorrow. So the value of one fish tomorrow is just 1 over R today. That's all we're trying to say. So the price of C1, if there's one fish today, the price of C2 today would be just 1 over R. That's it. Did that make sense?
Yes.
Okay. Let me go back to my PDF. Perfect. Okay, so that's the logic. Even if you don't want to like remember it that way, just remember that this would always be the case. If you solve this on the right hand side, you see this is just equal to minus R, right? If you just take the R above in the numerator, you can also always just blindly write that. If you don't want to remember what I just said, minus price of C1 over price of C2 will always be equal to minus R. Just remember that. If you think what I said was too confusing to understand, that also works. Yeah, so, and when you solve this, you get a relation between C2 and C1. So this is what you get. And again, I did not plug in the value of R as 2 just yet, because it's always to solve in a general term, in general like way, and then just plug in different values of R later. Okay, so
Excuse me.
yeah, go ahead.
How did you get C2 again? Where did you plug in?
This, oh, I just like solved the condition we usually solve. So MRS is equal to minus marginal utility of C1 over marginal utility of C2 equals to minus price of C1 over price of C2, which is just this. And I just like solved this and this. I just equated these two.
Oh, okay.
And
Thank
yeah,
you.
that gave me this. Cool. Okay, so the first question says R is equal to 2. How much fish does Bob consume in each period? So if R is equal to 2, I just put R equals to 2 here. That gives me C1 equals to C2. And I put this back into our budget constraint like we always do. So our budget constraint is C1 times R2. So C1 times 2 plus C2, which is just C1. So C2 times C1 plus C1 is equal to 600 times R. And R is just 2. So if you solve this, you get a value for C1. And so you just put it back here, and that also gives you value for C2. And you see the utility level for this bundle is 30. Once again, always solve for utility, helps in other parts. Okay, let's see what part 2 asks. If Bob can hire Common, a professional fish farmer, to take care of the pond, in which case the fish will reproduce at a rate of R equals to 4. To compensate Common, Bob has to give some fish in the first period. What is the maximum amount of fish Bob is willing to give? So again, let's see what this question is trying to ask. Obviously, Bob doesn't want to reduce his utility, right? Bob would not want to reduce the level of satisfaction. So by keeping the same level of satisfaction, what is the amount of fish Bob is willing to give to Carmen to increase the reproduction rate of the fish, but the utility of Bob remains the same? So it's another expenditure minimization problem. So let's see, you have R equals to 4, right? And let the amount of fish that you give to Carmen in the first period be X. So what does a constraint look like now? So in C2, what I can consume is 600 minus what I consume in period 1 minus what I give to Corman in period 1, and I multiply that by R. This is what I have left in time 1. I multiply that by time R, and that gives me how much I can consume in time 2. So that's a constraint now. And once again, we solved our MRS condition, and we get this, right? So for a new level of R, I just plug in the value of R. That's C1 times 4 square over 4. And that gives me C2 equals to 4 times C1. So we have a new relation in this case. And remember, we wanted the utility of Bob to remain the same, right? So we wanted the utility to be 30. And so the utility function, I just plug in this relation and I equate it to 30 because we want our utility level to be fixed at 30. And what was the utility function? It was just root C1 plus 0.5 root C2, and C2 we found is just 4 times C1. And we solve these two equations and you get two values.
Sorry, one question. Is the utility equals 30, is that the utility from question 1?
Yes. So
yeah, it is. All right.
yeah. No worries. Yeah, so we solve for this, and so now we have our values for C1 and C2. We need to solve for X. All I do is plug in the values of C1 and C2 in our budget constraint, and that gives me the value for my X variable. So 225, which is C1 times 4, which is R, plus C2, which is 900, is equal to 600 minus X times R, which is 4. And that gives me a value of X is 150. So Bob is willing to give Corman 150 pounds of fish in period 1 to get a higher reproduction rate of 4 while maintaining his utility at 30. So that was part 2. Let's see what part 3 asks. Bob's twin sister has a larger pond with more fish in the first period than Bob. And she takes care of her own pond as well. So R is equal to 2 again. Her preferences are identical to Bob's, and we assume their utilities are comparable. If Corman in 2 were to take care of Bob's pond for free, Bob would just be as happy as his sister. How much more fish there is in his sister's pond? Okay, now this question might look a bit confusing, so let's break it down and see what it means. Okay, so all question 3 is saying is, if you do not give any fish to Corman, right? So Corman takes care of your pond for free. How much utility do you get? Let's solve for that first. So again, you have a budget constraint, or I just plug in the value of R in a general relation, and we get C2 equals to 4C1. So remember, R is 4 here, but you are not giving any fish to Corman because Corman is taking care of your pond for free. So you still have a higher reproduction, but you're not giving any extra fish to anyone. So I get C2 equals to 4C1. I plug this back into the budget constraint, and we get two values for C1 and C2 again. And now we solve for utility. So this is how happy Bob is if Corman takes care of the pond for free. Now the question says, Bob's sister's utility is also 20 root 3. Remember, the question says, if Corman in 2 were to take care of Bob's pond for free, which we just calculated, Bob would be just as happy as his sister. So that means Bob's twin sister also has the same level of utility, that is 20 root 3. But the sister takes care of the pond herself. So for the sister, the R is equal to 2. So you see, this is an expenditure minimization question, again, where we fix the utility level at 20 root 3. We have an R. What we do need to figure out is how much fish does Corman have? So we'll see how we solve for that. So again, the general relation was this. I put R equals to 2 because the sister takes care of the pond herself, and you get C2 equals to C1. And remember, we want to fix the utility at 20 root 3 for the sister. So it's 20 root 3 equals root C1 plus 0.5 root C2, which is just C1. And you solve this, you get two values of C1 and C2. So now you have C1 and C2, and let's say W is the amount of fish Bob's sister has. And remember what the budget constraint looks like. So C1 times R plus C2 is equal to, now we don't know the number of fishes that the sister has. What we do know is we just solved for C1 and C2 given the amount of utility the sister has. So we just plug in the values of C1 and C2 and compare it to W times R, which is 2 for the sister, and you get W as 800. So the sister has 800 fish, and remember, Bob had 600 pounds of fish. So the excess fish that the sister has is just the difference. So Bob's sister has 200 more pounds of fish. Is there any doubt about that question? Okay, great. Oh, and then again, the last part asks, how would you relate your answers to compensating variation and equivalent variation? And the answer is compensating variation is minus 150 and equivalent variation is 200. The reason for that is again the same. Remember that compensate CV is just how you maintain the new utility at the old price. So let's see. That's what we did in question 2. We said we want to maintain 30, which is our original utility from part 1, at the new price. So the price here is the new R, which is R is equal to 4 now. How do we do that? By reducing. So again, we don't have money in the situation, right? So it's the change in your endowment. So we reduce our fish by 150 by giving it to Corman to maintain the same level of utility of 30. So that's your compensating variation. And what was the definition of equivalent variation? It was how do we maintain the new utility at the old price? So remember, the new utility, so the new utility was 20 root 3, right? And this was done. So if we fix the new utility at the old price, so what's the old price? The old R, which is R equals to 2. And we also solved for that. We did it for Bob's sister, right? So you maintain the utility at 20 root 3, so new utility at the old price, so R equal to 2. And we saw the excess fish we need is 200. So since this is the extra fish we need, it's a positive value. And since this is the fish that we're giving away, it's a negative value. So that's the reason, well, for those values. Okay, any doubt regarding the topics we have done so far? Any doubt regarding any examples we have done so far? Because now I'll be moving into the end. Yeah, go ahead.
All examples, like you said that you had checked past finals and you are doing the questions that show up often, right? Are you doing like all the questions that show up often?
No, so the way you'll see the final is that you have
like, I mean, are you doing all the types of questions?
Yeah, so you have four questions. One of them is definitely going to be an Edgeworth box question. One of them is definitely going to be an intertemporal change. So period 1, period 2. One of them is definitely going to be consumption and leisure. So the first question is usually a small question with less weight put on it. So it can be a budget constraint question, simple utility maximization question, anything. So I don't know about that. Like that's up to the prof. What I do know for sure is the other three questions that you will get. So it'll definitely be three of these. So I did the intertemporal change just now. For consumption and leisure, we covered both the possible questions. So one where the wage changes and one where the tax changes. And now we'll do the Edgeworth-Fox question, which would usually be the fourth question on your final.
Okay, great, thank you.
Okay, cool. So this is the last topic that we'll be doing today and the last question. So the logic here is that you have an exchange economy where you have two people and you have two goods. So two consumers, two goods, and each of them has an initial bundle. And you have a fixed amount of goods in the economy. So let's say A and B are the two consumers in the economy, and you have two amounts of goods that are fixed in the economy. So the amount of good one that consumer A has plus the amount of good one that consumer B has gives you the fixed level of goods that you have in the economy. So if person A has 10 units of good one and person B has 20 units of good one, then you have 30 units of good one in the economy, and that's fixed. And the same goes for good two. Now, what we try to answer is that if they have a certain bundle at the beginning of the economy, is there a way where we can make both consumers happier without hurting either one of them? So is there a possible way to exchange goods between them such that both of them are a little better than before, or at least one of them is, but we do not hurt any one of them? So that's what we try to find. And before we move into the question, there are a few concepts. So Pareto dominating outcomes, what are those? They are just the outcomes that make one or both, so either one or both the consumers better without hurting either of them. So that's the area between the indifference curves, and we'll see what that means. And Pareto efficient or Pareto optimal outcomes are the Pareto dominating outcomes that we talked about, but you have one extra condition, and that is the indifference curves need to be tangent to each other. So the marginal rate of substitution for A needs to be equal to the marginal rate of substitution for B, which is the slope of both of their indifference curves. And we see what that means in this figure. So you have a box where your x-axis is just the level of goods you have. This is supposed to be x1 and this is supposed to be x2. That's my bad. I also need to correct that. I'll take a note of that. Good. Yeah, so my bad again. So this is just the amount of x1 you have in the economy, and this should be the amount of x2 you have in the economy. And so the purple one is your indifference curve for A, and B is the indifference, and the red one is the indifference curve you have for B, because it's a convex indifference curve. So I'm just assuming Cobb Douglas here. You can have any sort of indifference curve, but this is the easiest to like see for this example. And so you have an initial endowment, right? So let's say this point right here is where their initial endowment was. So always remember, both of the indifference curves would pass through the endowment point, because that particular bundle is on B's indifference curve, but also on A's indifference curve. So the same point has both indifference curves passing through that point. So that's the first thing. Now we look at Pareto dominating outcomes. These are the outcomes that are just in the intersection of the two indifference curves. And what we mean by that is any bundle in this shaded region will make either A or B or both a little better, right? Because for A, which is the purple indifference curve, you move farther away from your current indifference curve, right? So you make A a little better. Same for B. So if you switch the box upside down, so for B, moving towards A is improving B's happiness. So again, the more you move inside this Pareto dominating shaded region, the better are both the consumers. And any doubts regarding that? Okay, cool. And so what are Pareto efficient outcomes? Pareto efficient outcomes are the ones that are dominating, so in the shaded area, but where the slopes are equal. So if you carefully notice, you can only have indifference curves tangent at points between x and y, because at any other point you would have an intersecting indifference curve and not a tangent one, right? So efficient outcomes are just where your slope of the indifference curves are equal within this shaded region. So that's Pareto efficient outcomes. And a contract curve is just a curve in your box which plots all the possible points where your indifference curves can be tangent. So why do we look at these three things? It's simple. First, we figure out, is there a Pareto dominating region? Is there a possibility that we can make both consumers or at least one better? Then we see all the points where they can be tangent, the indifference curves can be tangent. And then we see for all those points of tangency, what points lie in this shaded region. And that gives us our Pareto efficient outcomes. So all these three things work in a synergy. So that's the basis. And before we start the question, what are we trying to solve? So you see, consumers take prices as given in a competitive economy. And given the prices, they try to maximize their utility. So again, a simple utility maximization. But the problem here is your budget constraints are a little different to interpret. They're the same, but there's a sort of nuance in the interpretation. And it is that, so the price I spend on good one, the price I spend on good one, plus the price I spend on good two should be equal to what I spend on my initial endowment. So the amount of money I'm initially spending in the economy is constant, right? So if this was my endowment of good one, and this was my endowment of good two, the total money I spend on this bundle has to be same as the money that I spend on any other combination of bundles in this economy, because I have a fixed amount of money with me. So that's how we interpret budget constraint here. By the way, is anyone on unmute? I think I just want to make sure like the recording is not messed up. Okay, cool. And okay, so this is the important part. So this is how you always solve an Edgeworth question. And it's always easier to follow these steps. It's what I did when I used to solve Edgeworth questions. The first thing, obviously, always draw the box. The second thing you do is you plot the indifference curves for both the consumers. The third thing you do is you plot the contract curve. Once again, what's the contract curve? It's all the points where you can have both indifference curves tangent. So it's the equation such that the slope of A's indifference curve is equal to slope of B's indifference curves. And it's a set of all those points. So it's a line that shows all those points. The fourth thing we do is once we have all of that, we solve for utilities for A and B. We maximize utilities of A and B. And you can do it two ways. You can use P1 and P2 as variables. That's also fine. What I usually do is fix the level of price of good 2 as 1. So because we are only interested in the ratio of prices, we're not interested in the price itself. So it would give you the same result. So it's just easier to assume the price of second good as 1. And then it makes the calculations a lot easier. Okay. The fifth step is, so step 4 will give you an equilibrium in the economy, right? It will give you an equilibrium price ratio, and it will also give you an equilibrium allocation of goods between the two consumers. And sixth is, now we know what the equilibrium looks like. We see what happens if one of the consumers gets to dictate the price. So if one of them is allowed to dictate the price, we'll see, is that efficient? Is that Pareto efficient? And is that an equilibrium? We'll see that. Okay. So this question is not from a final, and there's a reason for that. The question on the final is exactly the same, but it's a little easier in some sense. And I'll explain what that is. This is a little, not difficult, I would say it's a little more complex compared to the final problem. But if you know this, the final problem should be a piece of cake. Okay, so let's see. So you have Coleman and Dobbin, and they consume cheese and wine. Coleman's utility function is log of C plus W. Dobbin's utility function is C squared times W. And you have their initial endowment. So Coleman has 38 pounds of cheese, 3 liters of wine, and Dobbin has no cheese and 27 liters of wine. First part is draw the Edgeworth box and shade all allocations that Pareto dominate the initial endowment. So let's do that. So what's the indifference curve for Coleman? You have an initial bundle that Coleman has. You calculate the utility level. That is 6.64. So the indifference curve for Coleman should give an utility level of 6.64 across all points on the indifference curve. So you just equate that to this number. So ln of cheese plus wine, so ln of C plus W equals to 6.64, and you just plot that equation. I guess now you have access to online graphical calculators and like online graphing tools, so it'll be easier, I guess. But the way you do it, you have you calculate the utility at your endowment level, and then that utility has to be same on your entire indifference curve. So you just form an equation for that. And you do the same for Dobbin. So Dobbin has 0 cheese and 27 liters of wine, right? Yeah. And so Dobbin's utility is 0 squared times 27. So just 0, right? So notice that for a function which is C squared times W, the only way you can have that equal to 0 is that either C is 0 or D is 0, right? So either cheese is 0 or either wine is 0. So this is what your Edgeworth box will look like. Coleman's indifference curve is you just plot different points And all of these give the same level of utility, which is 6.64. And for Dobbin, either cheese is 0 or wine is 0. So it's just the two axes that you have. So that's the indifference curve for Dobbin. And the area which is in between the two indifference curves are all Pareto dominating outcomes. And let's see what the next part asks. Draw the contract curve and find the comparative equilibrium price station allocation. This is the question which would be the most important in the Edgeworth box questions. So step 1, again, we find
Sorry.
Yeah, go ahead.
How did you get like those different points for Carmen, like for the blue lines?
For this, so what's Carmen's indifference curve? It's log of C plus W, right? So you equate that to 6.64, which is the utility level that needs to be constant along all the indifference curve. So you just you can use a graphing calculator and graph it online. I just got it from my TA's notes from last year. But the easiest way to do is when you have two variables and that's equal to a constant, put one of the variables as 0 or 1 and then see what value the other variable gives. And keep on switching values from 0 to 1 to 2. And that should give you a set of points, and then you just plot that. If that's not comfortable, now you have access to online tools. Just plug in the equation and you'll get a curve. As simple as that.
Okay, great.
Yeah. So yeah, once you plot these, again, this is a relatively harder thing to plot, which is why I said once you get the logic, on the exam, you'll probably get like an easier indifference curve to plot. But yeah, that's that. So step, again, what was the step we decided? We draw the contract curve now. So contract curves is basically all the points where slopes of the indifference curves are equal. So what's the marginal rate of substitution for common? It's marginal utility of C over marginal utility of W. So 1 over C over 1. That gives you 1 over C. And we do the same thing for Dobbin. So marginal utility of C. Wait, where is the? Yeah, so marginal utility of C over marginal utility of W. And that gives you this. But what's important to note is that you have 3 variables here, right? To plot the contract curve here, you need WC, which is wine of Corman, as a function of the cheese that Corman has. So you can easily plot something, right? But you can't plot something with 3 variables on a 2D graph. So this is what was complex about this question. In the exam, as I've seen from the past finals, one of these two sides would be a constant. So you'll get WD and CD, and there'll be a constant here. Or usually what will happen is you have C, cheese of Corman, and then Corman's wine, and that will be equal to a constant. So one of these things would be a constant, and that makes your problem much easier. But I just wanted to make sure like everyone knows what to do if you have such a situation, and it's not too hard. What you do is remember that the economy has fixed number of goods, right? So you have 38 wait, was it? Yeah, you have 38 pounds of cheese and 30 liters of wine in the economy. So the sum of whatever cheese Corman has and whatever cheese Dobbin has to be 38. So this plus this needs to be 38. So I just write the cheese that Dobbin has in terms of the cheese that Corman has using this endowment equation. And I do the same thing for WD, which is the wine that Dobbin has. It's just 30, which is the total wine in the economy, minus whatever wine Common has. That's what Dobbin has, right? Because you have fixed goods. And I just plug these two values right back into this equation. So now you see I have an equation with the two variables we need. And I just simplified this. And the equation I get is this. So this is the equation of the contract curve that we need. And when you plot that, you'll see this is what you get. Again, you don't need to plot it like this. The easiest way to do is plug one of these values as 0 and see what you get for the other value. So if I put WC as 0, you'll get C as 0.62. Or what you can also do is plug in the maximum values for one of them. So if I plug 30 for wine, I can equate it to get a value of C, or the other way around. It's just a lot of plugging in values to see what the curve looks like. And I know that can be like a little tedious, but that's how it's done. There's no like magical way to do it. You'll have to plot points and see what the curve looks like. Sorry about that. Okay. What was next? Now we need to find the comparative equilibrium. So how does that work? So again, you have a utility problem. You need to maximize that. And you have a constraint, right? So this is given to us. And remember what we talked about the constraint. You have the price of C times the cheese that Common has. And we assume the second price to be equal to 1, because that just makes things easier for us, because we are anyway interested in the ratio. And whatever you spend on the two goods has to be equal to whatever you're spending on those goods right now. So Common has 38 pounds of cheese. Whatever Common spends on cheese plus whatever Common spends on wine, that total amount needs to be constant throughout. So this is how your budget constraint is now functioned. So what's the step 1 in a utility maximization problem? The marginal rate of substitution has to be equal to the ratio of prices, right? So what was the marginal rate of substitution for Common? That's marginal utility of C over marginal utility of W, that's 1 over C, times the price is equal to the price of good 1, which is just P, and we assume the price of good 2 to be 1. So that's P over 1, that's just P. And that gives you a relation. So this is the first equation you have. And now you replace this in the budget constraint. So when you replace this in the budget constraint, you get two values of C and W in terms of P. So we still don't know what the equilibrium price is, right? But we are trying to solve for a bundle of goods that gives us an answer in terms of the price. And we'll see why we're doing that in a bit. So you get two solutions from here, which is the equilibrium cheese for Common and the equilibrium wine for Common. Now we do the exact same thing for Dobbin. So you maximize the problem, and your budget constraint is just what you spend on C, which is cheese, plus whatever you spend on wine, times what you were initially spending with your original bundle. So Dobbin had no cheese, so nothing on cheese, and had 27 liters of wine. So that's 27 times 1, because we assumed price of wine to be 1. So that's 27. And now you do the same thing again. You solve the maximization problem. The marginal rate of substitution equal to the ratio of prices, and you get another relation. And you do the same thing. You find optimal allocations in terms of price. This is just coincidentally a constant. It could also be in terms of price, but don't worry about that. And now we have 1, 2, 3, 4 variables, and all are in terms of P. how do we solve for P? Pretty easy. It's the easiest part in the problem. You know that the total amount of wine or total amount of cheese in an economy is fixed. So WC, the wine that Common has, plus WD, the wine that Dobbin has, needs to be equal to 30 because it's fixed. And since we have these values in terms of the price now, just plug in those values and you get a value for P. You can also do the same thing with cheese, where you would just write 1 over P plus 18 over P should be equal to 38 because you only have 38 pounds of cheese in the economy. You would get the same value. And since this is the price of C, when you take the ratio, that is price of C over price of wine, so that's 1 over 2 over 1, you get the ratio as 1 over 2. So now you see why we took one of them as 1. And it's usually easy to take the second price as 1. So the answer just gives you the ratio directly because it would just be this over 1, which is the value itself. So it's always easy to assume the second price as 1. And now you have the value for P. Just plug it in your original equations that you earlier derived that were in terms of P. But now you have the value, so just plug 1 by 2 and you get these values. So that's your comparative equilibrium. This is the final solution that we're looking for. Any doubts regarding that? I know this is like a lot of information to take in such a small amount of time. Okay, I'm gonna assume that everybody's fine with that. And now the last thing that the question asks is, if Dobbin can dictate the price ratio, what price ratio will he choose? And is this Pareto efficient? This is not that hard if you understand the logic behind it. So if Dobbin dictates the price, Carmen has to take the prices given, right? So for Carmen, her utility maximization is still the same. So Carmen has the prices given. It's the same values we found earlier. But for Dobbin will take what's left after Carmen consumes and then maximize utility and decide the price according to that. So for Dobbin, it's no longer what Dobbin had earlier. That was 18 over P and this equals to 9. That's not what Dobbin has anymore. Dobbin has whatever Carmen takes, that's 1 minus P, and subtracts it from the total amount available in the economy. Does the same for both the goods. And now he chooses to maximize his utility. So now your utility function is no longer this. Your utility function is now in terms of P, because Dobbin wants to maximize his utility by dictating the price. So that's how he does that. So same, it's a utility maximization problem. You can solve this as you want by taking the modulator substitution. That would be a little difficult. So in this situation, taking the Lagrangian is easier. I didn't get time to rectify the notes here, but this is how the TS solved it, and it's the same. You just set up the Lagrangian and you solve the utility maximization problem. So there's that. This is a rather tough maximization problem. You would not see such a problem in the exam. I haven't seen one. It's very calculation efficient, the exam. So it'll probably be an easier function of P here. So you don't have to do all of this. It'll just be an easier calculation. But once you solve this maximization problem, you will have the price ratio as 7 by 38. So you see this. So with this price, your new allocation when Dobbin dictates the economy is this. And now you want to see, is this Pareto efficient? And the way you see that is you compute the marginal rate of substitution for Corman and equate it with the modulator substitution of Dobbin. And if they're not equal, then it's not efficient because your indifference curves are not tangent. If these values are equal, then you can say your the position you have now is Pareto efficient. Any doubts regarding this part? Okay, I think that was the last of our questions. I wish everyone best of luck for their exams. I hope this session helped. I'm going to stop recording.